Okay, let's move on. In the last class, we have started to discuss the wave-particle dualism, and we saw that the wave-particle dualism was first discovered for the photon. Only later on, it was discovered that the wave-particle dualism also exists for other massive particles, including the electron. So any particle with a mass m and a velocity v would have a wavelength which is associated with this particle, and the wavelength would be expressed through this formula here. So the wavelength would be the Planck constant over the mass of the particle times the velocity of the particle. So now the question was, how could the atomic model be described more precisely, taking the wave-particle dualism of the electron into account, thereby overcoming the shortcomings associated with the Bohr atom model. And since the Bohr atom model already introduced the quantization of the states of the electron, physicists looked into areas of physics where waves would be quantized. And an area of physics that deals with waves that are quantized are so-called standing waves. So standing waves are a very common phenomenon. For instance, you produce a standing wave when you pluck a guitar string, and then your guitar string vibrates up and down, and only certain frequencies are allowed, and that means also only certain wavelengths of the waves that are associated with these vibrations are allowed. And actually, these waves are being quantized. Okay, so you see here a few standing waves as they can occur when you pluck a guitar string. So the wave which has the longest wavelength, that is the so-called ground vibration. And you see that vibration here. And you see that the wavelength associated with that wave is 2 times the length of the guitar string if we consider this distance here between this point and that point as the length of the guitar string. Okay, so now then there are also other higher harmonics allowed. This is the first one, and you see that for this one, the wavelength of the wave is equal to the length of the guitar string. Okay, then we have other higher harmonics associated with shorter wavelengths. So this one here is associated with the wavelength with 2/3 of the length of the guitar string. This one here has a wavelength which is half of the length of the guitar string, and so on. Okay, so this means that these standing waves are obviously quantized with regards to the allowed wavelength. So now we can describe the allowed wavelengths using a very simple formula and using quantum numbers. Okay, and this formula is shown here. So the general wavelength of an allowed standing matter wave is 2 times the length of the guitar string over a quantum number n, whereby again quantum number means nothing else but integer number. Okay, so if we insert n equal to here, then we would get the wavelength for this vibration here. So we would have 2 times the length of the guitar string over 1. Well, that would be 2 times the length of the guitar string, okay, which is equal to the wavelength of that standing wave that you can see here. Okay, if you enter n equal to 2, well, then lambda will be 2L over 2, which is equal to L, and that would be the wavelength of the second allowed standing wave over here. So now one question is, what causes these standing waves? And the answer is that it is the confinement of the wave within the guitar string. Okay, so the guitar string has only a specific finite length, and for that reason, the wave is confined within the guitar string. And actually, the standing wave is produced by the interference of 2 waves that are traveling into opposite direction. So what happens when you plug a guitar string actually is that you trigger waves that are going from the point at which you plug the guitar string into 2 opposite directions. Okay, but now because the guitar string is pinned down, these 2 waves are getting reflected, now traveling into opposite directions. Okay, until they meet the end of the guitar string where they are getting reflected again. And now these 2 traveling waves, which are traveling in opposite direction, interfere. And that interference produces the standing wave. And by standing wave, we mean a wave which does not seem to move. And that means that all the troughs and the crests and the notes, they stay fixed at their position. Okay, you see that is true for all the 4 or 6 standing waves shown here. So here the crest and the trough of this first wave is fixed in the middle of the guitar string. For this wave here, this is also true. In addition to that, this wave here has a node, okay, where the algebraic sign of the wave changes, and you see that this node is also fixed at a fixed position on the guitar string. The same is true also for all the other standing waves. Okay, so for instance, this standing wave here has 2 nodes, one here and one over there, and you see that these nodes stay fixed on the position of the guitar string. They do not travel. Okay, so that means that a standing matter wave is actually an interference phenomenon of 2 waves that are traveling in different directions, and this is shown here. So here you see a negative traveling wave in red and a positive traveling wave, and you see here in blue the interference pattern for these 2 waves. Okay, so you see that both the red wave travels, and it travels from the right to the left, and you see that the green wave travels, and you see that it travels from the left to the right. But the addition of the 2 traveling waves giving the standing wave eliminates that traveling. Okay, you see that the standing wave in blue has crests and troughs and nodes which do not change their position. Okay, so now how could this concept of standing waves be applied to atomic theory? So when you consider that an electron in an atom, such a hydrogen atom, also has wave properties, then that wave associated with the electron would also be Yes, Joseph, you have a question?
Oh, yeah, thank you. Can I just, the way that you just described the standing wave as the difference between these two frequencies, is that, can you call it a beat?
Sorry?
Could you also call a standing wave a beat?
A what?
A beat, B-E-A-T?
A beat?
Yeah.
What is meant by a beat?
A beat in the definition, in the physics definition, is the difference of two frequencies.
No, it's not the difference between two frequencies. It's the addition of the amplitudes.
Oh, okay. Right,
So
right.
you add the amplitudes.
Oh, right.
Traveling.
I got you.
You do not
Exactly.
you do not add up the frequencies, okay?
The
Only
amplitudes.
the amplitudes.
Right. All right. Thank you.
Okay.
Yep. Got it.
All right. Okay. So now to the question, what does that have to do with atomic theory? Well, in an atom, like an hydrogen atom, you have electrons that are confined within that atom because the electrons are, well, bound to that atom. So now if the electron doesn't only have particle properties, but also wave properties, then there should be a wave associated with that electron. And that wave would be confined within the atom. Therefore, that wave, it should be possible to describe that wave as a standing wave. Okay? And now in the following, we want to develop how we can describe electrons within an atom as a standing wave. Okay, so now before we go to the actual atom itself, and we will stick with the hydrogen atom as the most simple atom here, we will first work on a simplified problem. And that simplified problem is an electron in a one-dimensional box. So an electron in a one-dimensional box travels necessarily on a line. Okay, so we have here schematically a one-dimensional box. Okay, and the walls of that box shall be infinitely high. Okay, so that electron can therefore not get out of that box. Okay, but within the box, the electron would be free to travel. Now the box is one-dimensional, and for that reason, that electron can travel only on a line back and forth within that box. Okay, so within that box, the potential energy of the electron will be zero. The electron will only have a kinetic energy because it can move within the box on that line. Okay, so now as the electron travels on that line, it can hit the wall, and when it hits the wall, it will be reflected from the wall traveling into the opposite direction. Okay, until it hits the opposite wall here, where it will again be reflected traveling into the opposite direction. Okay, so now we need to consider that our electron does not only have particle properties, but also has wave properties. So there should be waves associated with that particle that travel within that one-dimensional box. Okay, and as the electron as a particle will be reflected at the wall, the associated wave will also be reflected at the wall. So that, similar to, well, the situation that we just discussed with the guitar string, we would have two waves associated with the electron that would travel in opposite directions and that would interfere with each other to produce a standing wave. Okay, and we would expect that the frequencies of the standing wave would again be quantized, and of course then also the wavelength of the standing wave would be quantized. Okay, so the question is now, how can we describe this mathematically in an appropriate form? So in particular, how could we describe the standing wave which is associated with our electron? So the waves could be described using a wave function, and our task would be now to develop the wave function for the electron in the one-dimensional box. Okay, now in order to do this, we will use this differential equation here, which holds for standing waves in general. And it says nothing that, but that the second derivative of a wave function that describes a standing wave is equal to minus 2 pi over the wavelength of that standing wave square times the wave function that describes the standing wave. Okay, so now we must apply this equation to the electron. Okay, and we will do this now the following way. We know that the electron that travels in our one-dimensional box has a kinetic energy, and that kinetic energy will be given by the formula 1/2 times the mass of the electron times the velocity of the electron square. So now we can do a few mathematical rearrangements with that equation in order to be able to plug it into the de Broglie equation for the wave-particle dualism. So we can expand the numerator and the denominator by m. Okay, and if we do so, well, in the numerator we will have mv to the power of 2 square, and in the denominator we will have 2m. Okay, now we can solve this equation for mv square, and then mv square is equal to 2 times m times e, and then we can just take the square root of that, and then m times v is equal to the square root of 2 times m times e. So now we can use the de Broglie equation for the wave-particle dualism, which says that, well, the wavelength associated with the electron will be equal to the Planck constant over m times v. Okay, we can just solve this equation for m times v, then m times v is equal to h over lambda, and then we can substitute here this m times v by h over lambda, okay, and solve for lambda, and then lambda is equal to h over the square root of 2me. So now we have the wavelength for the electron, which we now can plug into this differential equation here. Okay, so we substitute lambda here by this term over there, and this differential equation then becomes d square psi over dx square is equal to 4 pi square em2 over h square times psi. So now we can do another small mathematical rearrangement and bring E, which is the kinetic energy, to the right side, okay, then we have it over here, and then the equation is d square over dx square times minus h square over 8 pi square m times psi is the kinetic energy times psi. So this is now nothing else but the Schrödinger equation for the electron in the one-dimensional box. And the equation says nothing else but the operator of the kinetic energy, which is this term here, multiplied with the wave function for the electron in the one-dimensional box, gives you the kinetic energy of the electron within the one-dimensional box. Okay, now what we're really interested in is to find out what are the wave functions that describe the electron in the one-dimensional box. In order to get that, we need to solve the Schrödinger equation for the electron in the one-dimensional box. So one way to solve a differential equation is to guess the answer or guess the solution and then show that the solution is actually correct. And this is the path that we take here. So a very general solution for this equation would be the following. We would just assume that a solution is that we have a sinus term plus a cosinus term, and these sinus terms would have generic coefficients r and s in front of the coordinate x in the one-dimensional box, and the general coefficients a and b in front of the sinus and the cosinus terms respectively. So this would be a very generic wave function describing a very generic wave. So now we need to think about boundary conditions for that wave in order to make our wave function more specific to our problem. And the first boundary condition that we will introduce is now that the wave function must be 0 when x is equal to 0. So this means nothing else but that the amplitude of the wave function must be 0 when x is equal to 0. Okay, so that makes sense because at x equal to 0, the electron hits the wall and gets reflected, and therefore it makes sense to assume that the amplitude of the wave function at this position would be 0 as well. So now this means that the coefficient b must be 0, because otherwise the cosinus term here would prevent the wave function to become 0 at x equal to 0. And this is just a property of a cosinus term in general. So that our wave function would simplify to this form here, and it would be equal to this coefficient a times sinus rx. Okay, so now we still need to determine what a is and what r is. And in order to determine what r is, we now introduce a second boundary condition. And that second boundary condition says that psi must also be 0 when x is equal to a. Okay, whereby a is nothing else but the end of the one-dimensional box. So a is equal to the length of the one-dimensional box. Okay, so this is also a boundary condition that we can assume for the standing matter waves that we are looking for, because for a standing matter wave, not only the amplitude needs to be 0 at x is equal to 0, but also at x is equal to a. And that should be true for all the standing matter waves. All right. So now this means that r times a must be equal to n times pi, because only at values of pi and integer multiples of pi, a sinus term becomes 0. So now we can just solve this equation here then for r, and then r is equal to n times pi over a, which now means that we have found the value for r. And our wave function becomes even more specific. It now has the form psi is equal to a times sinus of n times pi times x over a. Okay? And now you see that our wave function contains a quantum number, the quantum number n, which shows that our wave function is actually quantized. Okay, and for each different quantum number n, we would get a different wave function describing a different standing wave. So for n is equal to 1 and n is equal to 7, the waves are being shown here. So for n equal to 1, our wave has the longest wavelength. For an n equal to 2, we have one node. For n and the wavelength becomes shorter. For n equal to 3, we have then 2 nodes. For n equal to 4, our wave has 3 nodes. For n equal to 5, our wave has 5 nodes, and so on. So these wave functions would basically describe the allowed states of the electron in the one-dimensional box. Okay, the allowed waves for the electron in the one-dimensional box. So we're still not quite finished, because we still do not know this parameter a here. So in order to find this parameter, we need to introduce a third boundary condition, which says nothing else but that the probability to find the electron somewhere in that one-dimensional box must be 100%, because the electron can never leave our one-dimensional box. So this requires now that we consider the square of the wave function, which gives the probability to find the electron at a position, at a specific position within the one-dimensional box, when we consider the electron as a particle again. So this is the so-called Born interpretation of the wave function. Okay, the square of the wave function gives you the probability to find the electron at a particular point within the one-dimensional box. So now if this is so, then the probability to find the electron with anywhere in the one-dimensional box will need to be 100%, and that's the case when the integral over psi square over the entire one-dimensional box is equal to 1. Okay, so that means that, well, a square times the integral from 0 to a over sinus square n times pi times x over a dx must be equal to 1. So when we solve this integral, and I'm omitting actually a number of mathematical steps here for clarity, and because of the fact that this is an inorganic chemistry course and not a physical chemistry course about quantum mechanics, then we will find that A has to be the square root of 2 over A. So this means that we now know the full wave function that fully describes our electron within the one-dimensional box, which is equal to the square root of 2 over A times sine S n times pi times x over A. Okay, so this coefficient here is called the normalization constant of the wave function, because it makes sure that a probability to find the electron somewhere in the one-dimensional box is 100%. Okay, so now let's go from this relatively simple problem of the electron in the one-dimensional box to the more complex problem of the electron in the hydrogen atom. So what are the similarities and what are the differences between the two problems? Well, the similarities are that similar to the electron in the one-dimensional box, the electron is confined, okay? It is confined in the one-dimensional box, but it's also confined within the atom because it's bound to the atom. And for that reason, again, we should be able to describe the electron in the hydrogen atom as a standing wave. But what are the differences? Well, the first difference is that in contrast to a one-dimensional problem, we have now a three-dimensional problem, because atom is spherical, so we have to consider three coordinates, x, y, and z, instead of only the coordinate x. And the second major difference is that we now also have a potential energy to consider. Okay, remember, the potential energy of the electron in the one-dimensional box was 0. The potential energy of an electron in an atom is not 0 because of the Coulomb attractions between the electron and the proton. Okay, so that gives the electron a potential energy. So that means that we have to expand the Schrödinger equation that we previously saw from one dimension to three dimension. And in addition to the operator for the kinetic energy, we also need now an operator for the potential energy. Okay? So you see here, we have now, instead of one coordinates, three coordinates, x, y, and z. And in addition to the operator for the kinetic energy here, we now also have an operator for the potential energy involving the three coordinates, taking the Coulomb interactions between the electron and the proton into account. Okay? But again, just like in the case before, when we apply that operator for the potential energy and the kinetic energy to the wave function, okay, then that gives us the energy of the wave function. Now that wave function would now be expected to be a three-dimensional wave function, not having only one coordinate, but three coordinates, x, y, z, and our standing wave that we would expect to be a solution of that Schrödinger equation would not be a one-dimensional standing wave, but a three-dimensional standing wave. Okay, so now in order to get the wave functions that describe the possible wave functions for the electron in the hydrogen atom, we need to solve that Schrödinger equation. So now we again have to think about boundary conditions for our standing matter wave that we would expect. So here are the two. Okay, so the first one would be that psi square would become 0 as r approaches infinite. That says nothing else but we would assume that if we go infinitely far away from the nucleus, that then the probability to find the electron would approach 0. Okay, and secondly, if we integrate over psi square, then that integral would again have to become 1 if we integrate over the entire space, because it would mean nothing else but that the probability to find the electron anywhere in the space must be 100%. Okay. So thirdly, we would also expect that our wave function describing the electron should be continuously differentiable and single valued. So with these three boundary conditions in mind, we would now want to solve this Schrödinger equation here. So now this is mathematically a significantly more complicated problem than the problem that we encountered associated with the electron in the one-dimensional box. So I again omit all the mathematical details here, and I refer you here to your physical chemistry courses, your quantum mechanics courses. I only want to describe the outline of how the Schrödinger equation can get solved. So it is mathematically easier to solve the Schrödinger equation when you switch from a Cartesian coordinate system to a spherical polar coordinate system. Okay. So in a Cartesian coordinate system, you describe a point in space by 3 coordinates x, y, and z. So now in a spherical polar coordinate system, you describe a coordinate via the distance, well, of a particular point from the origin, okay, which is r, and then 2 angles between the first one between the z-axis and, well, that line here that connects the point r with the origin, and this angle here, which is between the x coordinate and basically this line here, which results from the projection of this point in space here onto the xy plane. Okay, so in a nutshell, in a spherical polar coordinate system, you can describe a point in space using the distance of that point in space from the origin in 2 angles, theta and phi. So now, when you solve the Schrödinger equation in that spherical polar coordinate system, you also get your wave function that describes the electron in polar spherical in the polar spherical coordinates, and that is shown here. And the wave functions are now a product of these 3 functions here. So this function here is called the radial function, which is only a function of the distance of the electron from the nucleus. This function here is the collatitude function, which is a function of the angle theta. And this function here is called the azimuthal function, which is a function of the angle chi. Okay, now you see here the explicit mathematical forms for these three terms. And we do not need to understand all the details here. The only thing that we should realize is that the radial wave function is a function of, well, as I said, r, and it is the function of the quantum number n, as well as the, no, it's only the quantum number n. So this one here, the collatitude wave function, is a function which is a function of the quantum number m and the quantum number l. And here this azimuthal function is only a function of the quantum number m. So overall, and that's also another difference to the electron in the one-dimensional box problem, we need three quantum numbers in order to describe the electron instead of only one. And these three quantum numbers, they stand in certain relationships to each other. So n is called the principal quantum number 1 and can be any integer number larger than 0. So then there's the orbital quantum number L, and the orbital quantum number L can adopt values between 0 and n minus 1 for a specific quantum number n. So for instance, if the quantum number n is equal to 2, then L can adopt the values 0 and 1. If n, for instance, is 4, then L can vary between 0 and 3. So it can adopt the values 0, 1, 2, and 3. So thirdly, we have the magnetic quantum number m, and m can vary between minus L and plus L. And it can adopt any value between that. So for instance, if L is equal to 2, then m can vary between minus 2 and plus 2. It means that it can adopt the values minus 2, minus 1, 0, plus 1, and plus 2. Okay, if L, for instance, was 4, the magnetic quantum number m could vary between minus 4 and plus 4. Overall, it can adopt 7 values: minus 4, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Okay. All right. So now an electron in an atom is also described by a fourth quantum number, and that's the quantum number S. That's the so-called spin quantum number. But this spin quantum number is not an outcome of the solution of the Schrödinger equation. So in order to calculate the wave functions, you only need 3 quantum numbers. The fourth quantum number S was found independently. So for each wave function, there are 2 quantum numbers S possible, either plus a half or minus a half. And this quantum number S, or also called ms, is associated with the spin of the electron. So in this case, it helps again to view the electron as a particle, as a little sphere that can rotate around its own axis, and it can either rotate clockwise or it can rotate counterclockwise. And as it rotates, it produces a magnetic field. Okay. And that magnetic field can have basically two directions depending on the, well, direction of rotation. Okay. So either we can have the south pole pointing up and the north pole pointing down, or it is the other way around. So in this case, we talk about a spin up electron, and in this case, we talk about a spin down electron. Okay. So now the wave functions that we have just found, they have in chemistry a particular name. Do you know which name they have? They're being called also orbitals, okay? So the solutions of the Schrödinger equation are nothing but the orbitals that are associated with a particular atom, okay? So when we say that an electron is an orbital, okay, then that means actually the electron is in a particular state adopting a particular wave function. And of course, within an orbital, as you all know, an electron can adopt two spins, right? It can either be spin up or it can be spin down, and we can fill up to two electrons into the same orbit because what is called the Pauli principle, which says that no electron in an atom can have the same two quantum, it's the same four quantum numbers. Okay, let us stop at this point. In the next class, we will then go through all the different orbitals systematically and discuss their properties. So I can just stop the recording here.